Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is water supply. In this question, we're given that the country of Chefland has n cities with the capital being O, the city one, and unfortunately the only source of water in the entire country is the capital, that is city one. And so the water must be sent by pipes to all the other cities. And we're given that for each city I greater than 1, there's a unique city P of I less than I, such that there's a pipe connecting cities I and P of I. So basically, we are given a connected tree of something like this with the root node as the node 1. Now, over time, the pipes have degraded and all of them now leak water. The pipe connecting city I and P of I has a leakiness of A of I, which means that every AIth unit of water passing through it is lost entirely. So let us say this is the root node which supplies 20 units of water. So on each day, the capital city generates k units of water which goes to every city. So this 20 units of water will go to this city, will go to this city, will go to this city, this city, this city, and all the cities. But because of leakage, some water might get leaked on the way. So now let us denote R of I as the amount of water that is received by the ith city. So let us say we started from city 20. Now, this pipe leaks some water every fifth second. So, how much water will reach on city 2? So, that will be 20 minus 20 by 5, that is 4, right? So, 16 amount of water will reach till city 2, right? How much water will reach till city 3? 19, right? How much water will reach till city 5? 18 because 1 unit would be wasted. And similarly, 1 unit would be wasted on this part. So, 18 would reach here. Now, every 2 seconds, a unit is wasted. So, how much water will reach city 6? 16 by 2, that is 8, right? Now, how much will reach this city? 8 minus 8 by 4, that is 2. 8 minus 2, 6, right? How much water will reach till city 7? That would be 0, right? Because every second some water is dropping. So, all the water will get dropped and none of the water will be able to reach. So, this is what we'll get as our R of I, that how much water reaches each of the city in the end. And in city 1, there will always be 20 units of water, right? Because it does not have any leakage. Now we want to maximize the minimum value of all of these. So right now it is this 0 and we want to maximize it. And to achieve that, we can change at most any of the one pipeline. So if this is a pipeline, we can change this pipeline completely and fix it completely so that it has k plus 1 as its A of I, which would basically represent that there is no leakage because the water will be leaking at k plus 1 second, but by then all the water would have already gone, right? So this is pretty much the whole question. All we need to tell is the maximum possible value of this min value after fixing at most one pipe. So yeah, this is pretty much the whole question. Now let us see the test input once. So in the first input, 1 and 2 are connected and the city 1 is supplied with 43 units of water and every second 8 unit is lost. Now we can fix this pipe and make it 44. Now every 44th second 1 unit would be lost. So all these 43 units will reach the city 2. So it will also have 43 units and the min of this and this is 43. So the answer is 43. In the second input, this is the city we are given. Node 1 and 2 have a wastage every second and 1 and 3 have a wastage every 7 seconds. So if we fix this pipe, then the amount of water that will reach here would be 29 because there would be no wastage. Initially here there is 29 units of water and over here how much units would go? 29 minus 29 upon 7 and we'll take the floor of it. So this would be 4. So 29 minus 4, that is 25. So 25 units will reach the city. So this is pretty much the whole question. Now let us once move to the solution. So we are given that R of I is the water received by the ith city, right? Now, how would we calculate R of I? Let us forget about fixing the pipe for now and let us just see that how can we just calculate how much water will reach. So we'll start from the root node and the root node will have k amount of water, obviously. Now every other, so yeah, this is 1 by the way. Now every other I greater than 1 would have this much amount of water. That is the amount of water its parent had minus the amount of loss from parent to the current node I, right? And what would be that loss? The amount of water that was reachable till the parent upon A of I, that is how much water is leaking at what rate. Now, how can we solve this question? So, can we binary search on the answer? That is, we want to find the maximum x such that x is less than or equal to min of all of them, right? So, each of them have greater than or equal to the amount of this x, right? That is basically what we mean by this is every city has at least X amount of remaining water, right? And I hope that it intuitively makes sense on why it will work. It is a very, very common technique which we use when we want to like find the upper bound of some minimum of them or the maximum of them. And it's very easy to intuitively see on why it will work. You can formally prove it using induction, but I hope it's pretty clear on why we can apply binary search over here. Because if it is possible for some x, then for some lower x also it will always be possible, right? Like if we can achieve this maximum x, then for any x plus 1, it won't be possible. And for all the x from like 1 dot 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 x up till x minus 1, it would be possible to get that much score, right? I mean, this condition would be satisfied. So binary search is possible to do on x. Right. Now let us say this is some sort of our graph and we have computed R of I for each of these nodes, right? That is how much water will reach the ith node and we have already calculated it. And we are trying to find that how many of them can have at least X water, right? So there would be some nodes where X cannot reach, right? So let us say over here we have x1, x2, x3, x4, and x5 over these nodes. So r of x1 is less than x, r of x2 is also less than x, r of x3 is also less than x. So these are the nodes which we need to fix for this particular value of x, right? So if we can just increase the amount of water for all of these nodes, if we can increase the water that can reach to all of these nodes to something greater than or equal to x, we have a possible answer for x, right? So we need to find a pipe that will maximize for all of them, right? So we know that they all have less than x amount reachable, and we can easily calculate that, right? Now, if I fix this pipe, would it be useful? No, right? Because these may get fixed, but these all would never get fixed, right? What if I fix this node? Would anything help? No. The issue is in these nodes, right? I need to increase the amount of water reaching at these nodes. So fixing any of them won't be any beneficial, right? So now what if we see the LCA of them, right? So the only edges which I can fix or which I should be fixing would be all the edges from the LCA to the root node. So if this edge is maximizing the amount of water remaining, then I'll fix this edge. If this edge is maximizing the amount of water remaining, I'll fix this edge. And similarly, if there are other edges from the LCA to the root node, I'll fix them. And that would probably, like, I would fix the edge that would maximize the amount of water that reaches this LCA. Now, if maximum amount of water is reaching the LCA, I can just simply call my current algorithm, that is this one, that if I can get maximum amount of water at LCA, how much water would I be getting at all of these nodes? Because I've already fixed one of the edges above LCA. And by doing that, if all of my these values are now satisfied, then my current X is possible. That is, I can choose this X and I can increase my binary search. Otherwise, we need to decrease our binary search, right? Now, how would we calculate what is the maximum amount that can reach up till this LCA? So let dp of ij denote the maximum water from the root to the ith city that can reach by changing up to j number of pipes, where j will lie in between 0 and 1. Right. Now, how would we calculate dp of I0? This is nothing but whatever the parent could get, whatever the maximum parent could get without changing any pipe, minus the loss we get by coming from the parent to the current node, because we're not fixing any edge. Otherwise, if we are fixing some edge, so we have two options. Either take the one that is what was the maximum I could have got from the parent by changing one pipe, minus the loss I'll get by coming to this pipe, to this city. Otherwise, I just do not at all consider my parent. Like I just fix my current pipe. So if this is coming from, like from this city, if I'm coming to this city, I'll fix this pipe, and my amount of water, the maximum amount of water I can get at this city would be nothing but whatever I could have got at this city. That is nothing but the remaining at the parent of I. You can also write this in terms of dp, and that won't really matter. Like it would be nothing but dp of parent of I0. And yeah, if we compute this dp of ij for every node, and then we compute the LCA using any algorithm you wish, which can compute LCA in big of n time, we are fine. And if we compute the LCA, if we compute this DP array up till this LCA, we'll know that okay, what is the maximum amount of water I can get up till this LCA by changing at most one node, one edge, one pipe. And once we have got what is the maximum water we can get, we can just run our algorithm again to calculate the amount of water we'll be getting here, here, and at all of these nodes. And if at any point my R of I at any of these nodes is less than X, return false. Otherwise, if I'm able to get R of I greater than or equal to X for all the nodes, return true. And for all the other nodes, it's obviously already true, because if it was not true, they would have been part of the set, right? Because this set of these nodes contains the nodes where R of I was less than X already, right? Now, the time complexity of this overall solution is going to be big of n log A. Log K for binary search and big of n for doing everything on the tree. And yeah, that's pretty much the whole solution. Now let us see the solution in C++ and Python. So yeah, this is the solution in C++. We begin by creating the parent array. Begin by taking an input of the P and A. We create the DP array as we defined. So DP of I0 is this thing, DP of I1 is this, comma the max of whatever the parent could have already got, right? Like we do not do any, like we use the transition and we just do not get the loss. Now this count and n value up till here, all I am doing is calculating the LCA, that is the least common ancestor. And this is one of the methods of calculating LCA. And this works because we are given that P of I is less than I. So this is one method which you can use to calculate the LCA. And if you're not able to understand this, you can just use whatever algorithm of LCA you want. And this who will store the LCA. Now we'll define our new remaining array. This will store a new R. The root node will have this only, the K only. The LCA will have the maximum we can get by changing one pipeline. Now otherwise if it is not equal to LCA, we'll just run our normal algorithm, whatever it was. And if at any point the remaining amount, the reachable water till node I, even after fixing one pipeline, the best pipeline we could, if it is still less than X, we'll return false. Otherwise, we'll return true. And this is a normal binary search. And yeah, this is pretty much the whole solution. Now let us see the solution in Python. So we begin by taking in the input of nk and the input of p and a of I. Then we define a DP array. We do all the transitions and calculate the DP array as we discussed. Now this is a check function which will return true or false if it is possible to for this particular value of X, or if it is not possible. We'll define a count and this nval array. And up till here again, all we are doing is calculating what the LCA is. And again, you can use whatever algorithm you want to calculate the LCA. We are particularly using one of the algorithms which works because one is less than equal to P of I is less than I. You can just read more about this algorithm in the written editorial. Now, we define the n well of 0, that is the new reaching water, that how much water can reach after fixing one pipe, and we'll define the root node can still have k amount of water. Now, if the current node is equal to the LCA, we'll say that, okay, the maximum water which can reach up till here is the maximum water we could have from the root up till this node after fixing one pipe. And if I is not LCA, this is our normal algorithm, normal thing, how we were calculating the amount of water that will reach here, which is nothing but the amount of water that will reach up till the parent minus the loss. And if at any point this n well is less than x, we return false, otherwise we return true. And over here, this is nothing but a normal binary search function, and in the end, we'll print the answer. So yeah, this is pretty much the whole solution. I hope you liked it. Thanks. Bye.